I'm going to talk through um, I'm going to talk through like what was covered in lecture before we start the problem set. So uh, yeah, so first of all, we have this notion of a secant line. What we do is we take 2 points and we can construct a line from these 2 points, and then we can let the 2 points approach one another. And having them approach one another is going to visually look like this. So you can see that the lines are sort of tending towards, they're kind of approaching this line in green. And this line in green, you can imagine that it only crosses the curve at one point, which means that it's a tangent line. And now the derivative is just the slope of a tangent line. And that's the concept that we're trying to familiarize you guys with. So what's useful about this derivative is that, well, in real world applications, it is the idea of instantaneous rate of change. So it's like the idea of instantaneous velocity if you're talking about like a moving object. Okay. And well, symbolically, there's different ways of writing this. So we've got now this guy and this guy. These two limits are ways of expressing the idea of a derivative. So notice that here we have this slope. So from these 2 points, we can create an expression that calculates the slope of this secant line. And then if we just let y approach x, the slope of the secant line is going to approach the slope of the tangent line, which is exactly what this limit is doing. And then that is what we call the derivative, the slope of the tangent line at a particular point A. And this is just another way of saying the same exact thing. So what I'm going to do, Craig Spencer, he wrote it out in words why these two are the same, but I think it's a bit clearer if I just show you by drawing. So I'm going to draw for you what this is actually saying in pictures, and hopefully it will make a lot of sense to you in this way. So for this limit, we've really got 2 points. We've got A and we've got Y, and we have these, let's say these 2 points there. So this limit is really saying we let y approach a, and we're constructing this slope of the secant line, and then that's just going to converge into the slope of the tangent line. Okay, well, for the other limit, we can draw pretty much the same picture. The only difference is just a relabeling. So for this picture, we have a for this, and we have a plus h for this point. And so that's this a here and this a plus h there. And this limit as h goes to 0 is also just saying we're going to let the other endpoint approach. So h is just the discrepancy. It's the little step from one x value to the next. And when we let h go to 0, we're going to let the 2 points collide into one another. And what he's done here is he just said like this is a variable rewrite. So hopefully that makes sense. Yeah. And I think that the rest of this, let me see if I can actually just, okay, so that those linker, that's fine. So then the rest of this is really just the calculation work. So I just wanted to emphasize the concepts before we move on to the calculation. All right. So are there any questions? If not, then I guess we're going to focus on the problem set now. So, okay. So we left off with number 8. And we're given a graph, and we want to calculate these 2 things. We want to calculate n of -1 and n prime of -1. Right. So this is just reading information off of a graph. N of -1, that's just going to be the output of the function n. And notice that we're given that n is this function that's in bold. So we want to figure out what is the output at -1. So we plug in -1. We see the output is -4. -4. And then for part B, we have n prime of -1. So remember that n prime means derivative, means slope of the tangent line. So what we want to do is use a tangent line, and thankfully one has been provided to us. We have this dashed line right here. and we want to find the slope of it. Okay. Also, I guess you gotta need to check that this tangent line is tangent at the place -1, in which case it is. You can see it right there. It touches the curve at -1. Okay. And well, how do we calculate slope? We just need another point, and then we just figure out the slope. So if we go over by 1, we go down by 1. That tells us our slope for this line is -1. So that's pretty straightforward, right? And I think pretty much all the rest of the problems are just a bunch of algebra. We're using this limit definition of derivative. So you really want to get familiar with the limit definition, get it memorized. Yeah. So first of all, we have w prime of 2. Okay. This is what we want to compute. And we compute this using limit definition. So first of all, what does limit definition say? Limit as h goes to 0, w of 2 plus h minus w of 2 all over h. Right? It's something that you can kind of be able to repeat automatically. So normally we would have a here, but in this case, a is 2. It's the specific place where we want our tangent, or where we want our derivative to be. And then just expanded this out by definition. Okay, now we need to compute this guy. So what we do is we plug these values into our function w. Limit as h goes to 0. And we see that, well, we're going to need to square this quantity, and then we're going to need to distribute 2 plus h squared plus 3, 2 plus h. But otherwise, I'm basically just slotting it in. I'm slotting 2 plus h in for x in this definition. Okay. And then for w of 2, well, I'm not going to compute it. I'm just going to slot it in without thinking. So I'm just going to say 5 times 2 squared plus 3 times 2 plus 3. And the reason I'm doing that is because I expect a lot of cancellation. I actually kind of expect that all of these terms are going to cancel with terms in the first expression. Okay. And now we compute this limit. So algebraically, we need to simplify this. And the way we do that is we know that we need to distribute this 3. And we need to expand out this 2 plus h quantity squared. And so hopefully you're pretty comfortable with expanding something about, I guess it's called a binomial raised to the second power. You should know how to do that pretty quickly. I just did it. And then plus 6 plus 3h plus 3 minus 5.2 squared minus 3.2 minus 3. Okay, so I distributed the minus over each of those terms, which is another thing you're supposed to do. I think maybe I've seen people make that mistake before. So this minus, think of it as a -1. You're distributing -1 over each of the terms. Okay, and this is all over h. Right, and now we hope we can cancel, and we can. So first we have a +3 and a -3. Those will cancel. We have a +6 and a -6. Those will also cancel. And then 5 times 2 squared, 5 times 4. We see a 4 here, and 5 be multiplied outside. So those guys will cancel. And we're left with 3 terms. So let me clean this up a bit. We get limit as h goes to 0. 5 times 4h is 20h plus 5h squared plus 3h over h. Okay, and notice that all 3 of the terms in the numerator have an h in common. So we can actually cancel h in the denominator by those things. One way you'll see this written is that people will factor the h out from the numerator and then cancel the h's. That's one way to do it. Another way is you can imagine that the denominator gets split over all of the terms in the numerator. So we can, and that's kind of the way I prefer to think about it, because I'd rather not just factor an h out. That kind of introduces an extra step. So we can take this h and we can split it over each of those terms, and then we can cancel each of those terms individually. So we'll have 20h over h, which is 20, 5h squared over h, which is 5h, and then 3h over h, which is just 3. So we get 20 plus 5h plus 3. Okay. And now we can just take the limit. So this is going to turn into 23. Okay. Yeah, and I said this in the previous class, so let me also say this here. Notice that the real answer to this problem is not just the 23, but it's this whole process. Because this question is asking to use the limit definition of derivative. So we really want to see, firstly, that you have the limit definition derivative written somewhere, and also that we see all these algebraic steps that lead to the actual derivative. That shows us that you're actually using the limit definition. Okay, right. Now for part B. So find the equation for the tangent line at x equals 2. Right. Well, this w prime of 2 is a part of this tangent line. W prime of 2, slope of the tangent line at 2. This tells me that the slope is 23. We computed the slope just now for this tangent line. And what else do we need for a tangent line? Well, we also need a point that lies on the line. And if we want it to be tangent at 2, that tells us we want the point 2 comma something. We just need to calculate that something now, w of 2, which if we had actually calculated it from here, I don't know if my cursor is easy to see, but this would be w of 2. It's just that I didn't calculate it the first time around. But you can just imagine plugging it into this definition, calculating the value. So we get 5 times 4, 20, plus 6, plus 3. So we get 29. So the point that we have is 2 comma 29. And we can just use the point slope formula to write down the tangent line. Y minus 29 is equal to 23, x minus 2. And we don't need to do anything else to that. Any questions? So one more thing I'll say about this, though, is if you're ever not sure that what you calculate is correct, which that can happen, one thing you can do to check that this is a tangent line is you can just graph it, right? You have W, and you have what you claim to be a tangent line. So you can just, I don't know, open up Desmos or whatever calculator you want to use, and type in the function W, type in this thing that's supposed to be the tangent line, and just visually check that it looks tangent at the point specified at 2. And for this, it will. Okay. So just one way to check your work in case you don't know. All right. Next problem. Right. So you can basically ignore like the first 2 lines here. You don't really, all of this is just extra information that kind of just tells you 50 and 5. Wait, it's already right there. It's just kind of explaining in words like what those quantities are. So what we're really after is we're after h prime of 1, and we want to use the limit definition. So again, recall the limit definition, limit as, and now here we need to pause a little bit because we don't want to use h again, right? H is being used as the name of a function, height. So we want to use a different variable for h, and I'm going to use t. Okay, we let t go to 0. You can use whatever you want. I think some people would probably just use like delta h. I'll just write like delta h. So this is a capital delta, but I'm just going to use t. Okay. So, and now the rest of the definition says h of 1 plus t minus h of 1 all over t. Normally, remember, normally in the definition, we would have the h goes to 0, where h is the thing that we're limiting. In this case, we're limiting t, so I'm using t. All right, and now we plug in our function. So we have to use this function. We're going to need to plug 1 plus t into this function. You get a minus 16, 1 plus t quantity squared, plus 50, 1 plus t, plus 5 minus, and then I'm just going to plug 1 into this function. So minus 16 plus 50 plus 5. And again, I expect pretty much all of those terms to cancel. And this is all over t. Okay. Well, let's try to, should I mark them yet? Or maybe not, because I still need to distribute this. So let me just put in that extra step, minus 16. 1 plus 2t plus t squared. Make that look a bit more like a t. T squared. Plus 50 plus 50t plus 5, and I can distribute the minus. Why not? Plus 16 minus 50 minus 5 all over t. Okay, now let's figure out what we can cancel. 16 and the minus 16. Minus 50 and 50, minus 5 and 5. Okay, those are all the cancellations. Oh. Color. All right. Limit as t goes to 0. And now I can distribute this 16 over, and we have only 3 terms left in the numerator. That's good. So minus 32 t minus 16t squared plus 50t all over t. Okay, and again, notice each of the 3 terms has a t, so we can imagine distributing that denominator over each of the terms and canceling. So then this is going to simplify to limit as t goes to 0 of minus 32 minus 16t plus 50. And we can just take the limit. We can just plug in, and we'll get 50 minus 32, which is 18. Yes. Okay. And then lastly, notice that the problem actually gives units to us. So it gives us like feet and feet squared in seconds. So this is the rate of change of the height function. So we want to think of this as some kind of change of height over some kind of change in time. So our units are going to be feet per second. Okay. And for now, part B, this is a conceptual question. So I can actually ask you guys this. So given what we computed, part A, we found that the h prime of 1 is 18 feet per second. So is the ball going up or going down according to this? So if you want, you can message this in chat. Is the ball going up or going down? Okay, so I only got 2 answers. And you both think it's up, which is correct. Okay, so let's just make sure that you understand why. So you should be able to say this without uncertainty. All right. So h prime is the change. This is the change in height. So when we say that the height, well, really all we're checking is it positive or is it negative? Okay, if it's positive, then the change in height is positive, meaning that the height is increasing. So height is increasing in this case. Versus if the derivative is negative, that means that the height would be decreasing. Okay, and clearly 18 is a positive number, which means that the height is increasing, meaning that the ball is going up. So yes, for this problem, ball is going up. Okay, and I just want to make sure that the intuition here is not lost on you guys. So it's useful to be able to interpret um, all of this stuff sort of intuitively, because when you see calculus in practice, you're seeing it in applications, you're seeing it in physics, and describing things in reality. All of this stuff has like an intuitive explanation. They're just calculus is meant to just explain the world around you, basically. Anything that involves a rate of change of something, and quantities are always changing in life. So yeah, it's good to understand like, what the calculus is actually meaning. Anyway, um, right, number 11. So find the derivative of this function at x equals 5. So to make this problem look like all the other problems, we're going to give this function a name, call it f of x. So we're saying f of x is 1 over x, and the problem is asking us to calculate f prime of 5. Okay, so again, what does the limit definition say? Limit as h goes to 0 of f of 5 plus h minus f of 5 all over h. Okay. And so next we need to plug in our function. And this is where things get a little different. So our function is 1 over x. It's not a polynomial like the previous two problems. And so what we will get is actually going to be a complex fraction that we will have to simplify. So if I plug 5 plus h in for this, I'll get a 1 over 5 plus h. If I plug 5 in, I'm going to get a 1 over 5. But notice that they're both in the numerator, and we have an h in the denominator. So we actually have a big denominator, big over h right there. Okay. And so then you need to think, what technique do you use to simplify this so that you can actually calculate the limit? And well, Craig Spencer in I think the videos, he shows you a way to do it by splitting this denominator and then finding common denominators by subtracting fractions. That's one way to do it. I think it's slower. I'm going to show you the way that I found out, actually. I found out pretty recently. So instead, what you can do to really simplify things right away is try to multiply by something that will get rid of both of those denominators, those inner denominators. You want to get rid of them as fast as possible. One way to do that is you multiply by what will cancel, what will kill them off. 5 times 5 plus h. Okay. And well, you can't just arbitrarily multiply by something, so you have to multiply top and bottom by it. That way you end up not changing the expression at all. Right? This is just some fancy version of the number 1. Okay. Now, notice what happens when we distribute this quantity over. So when I multiply this into the first fraction, it's going to kill the denominator, and you're going to be left with 5. If I multiply it over to the second fraction, it's going to kill the 5. You're going to be left with 5 plus h. So let's go ahead and write that. So multiply over, we get 5 on top. Multiply the second one, we get a 5 plus h. Okay. And now here's an important thing. This minus is over this whole fraction, which means that this minus needs to be over this whole result. I need to put a parentheses there. Okay. If you don't do that, you're going to get the wrong answer. And hopefully it makes sense that this negative is supposed to be over both of that, because just imagine you take this, you multiply over. This negative was still in front of the whole fraction, so it should be still in front of the whole resulting expression. Okay. And now what about this denominator? Well, we can just multiply across 5 times h times 5 plus h. Okay. And right away, that has gotten rid of all this complicated fraction business. And now we just go ahead and simplify. So see that 5 and minus 5 will cancel, and you're going to be left with a minus h on top. Now, if you think ahead, you'll know that you can actually cancel the h on top with the h on the bottom. But I'm going to show one more step than I normally would, just because I know that people make this mistake. So if I first cancel the 5s, we'll have this. All right. And then you have this cancellation, this h on top and this h on the bottom. and you'll be left with a -1 in the numerator. Okay. But hopefully, like, you get to a point with your algebra where you can kind of see that and skip over this step and just be able to go straight to this. Okay. And then lastly, we can take the limit, just plug in. So we get -1 over 25. And yep, that's the answer we expect. Good. Okay, so any questions on this problem? No? Okay. Then we have 2 more problems before we're done for the day. Again, for this, I'm going to introduce a name for this function. So we want to find the tangent line to this at x equals 2. So the first thing we need to do is to calculate the derivative at 2. Very much the same thing we've been doing. So calculate first, the derivative at 2. And, well, recall limit definition because we're supposed to. Limit as h goes to 0 of f of 2 plus h minus f of 2 all over h. Okay, now we go ahead and just substitute in. So should I do it off to the side? I'll go down. Limit as h goes to 0. And now we need to do 2 plus h quantity cubed minus, I'll just say 8 over h. Okay. So now I guess I kind of tell a story because this 2 plus h cubed, I would like to hope that you know how to expand this right away, but I think more likely than not you don't know or you don't remember. So this is a story that I told the other class. So there's something called the binomial formula. And what that lets you do is it lets you remember how you expand just these expressions in general. So you've got this binomial x plus a, you're raising it to some power n, and there's actually a formula for how you expand this really quickly. And let me show you some examples of this formula. So for n equals 2, for squaring it, this you should definitely know. X squared plus 2ax plus a squared, right? And let me show you some more examples. X plus a cubed is x cubed plus 3ax squared plus 3a squared x plus plus a cubed. And maybe I'll show you one more example. Raising to the 4th is x to the 4 plus 4ax cubed plus 6a squared x squared plus 4a cubed x plus, I'm going to go on space. Did I do this right? Ax, yep, that's right. Plus a to the 4. Okay, and so like, yeah, you might ask like, how do I remember this stuff? And it's because there's actually some very nice patterns to it. The binomial formula, which you can just look up on Wikipedia, will show you these patterns. But the main thing to look at is actually, so each of these terms, if you count the number of a's and x's, it's always a constant number. So for this one, like you've got 4 a's and x's, 4 a's and x's, 4 a's and x's, all of them are 4 a's and x's. That's going to stay the same. And it's just that as you go from one term to the next, you're kind of pulling off one of the x's and turning it into an a. So the number of x's decreases, the number of a's increase. That's what's happening with those exponents. And then the other thing is, how do you remember the coefficients, the numbers in front? So this is where you draw the parallel to what is called Pascal's triangle. And that's actually something that you're probably shown in elementary school if you go to a good elementary school. 1 3 3 1 1 4 6 4 1. So the rule for generating Pascal's triangle is the next row is calculated by taking values from the previous row and adding them. So like, for example, this 4, I calculate by adding the numbers above it. So the 4 is supposed to kind of be sitting right in between. And so we calculate by just taking the 1 plus the 3. This 6 is the 3 plus the 3. 4 is 3 plus 1. And so you can imagine, like, what's the next row? 1, 5, 10, 10, 5, 1. All I'm doing is I'm just doing addition. But magically, these numbers actually encode the uh, coefficients for this expansion here. All right, so that's kind of the little trick that you use to memorize this kind of stuff. And so this raising to the third power is actually something that, if you know this trick, is very easy to do. Now let's go ahead and use this trick now. So I'm going to raise 2 to the third power. And then, well, the next thing is I remember Pascal's triangle, so we have 3 as the coefficient, leading coefficient. And then we have 2 squared times h, the next one. Basically, I'm recalling for the third power that the coefficients are 1, 3, 3, 1. It's very common thing. So then, and then 2 times h squared plus h cubed. And these 4 terms are the expansion of this 2 plus h quantity cubed. And then we tack on the minus 8 at the end. And then lastly, divide by h. Okay. And now we have some simple cancellation. And notice that the remaining 3 terms on top all have h in common, so we can cancel them with h in the denominator. And so we're left with 3 times 2 squared plus 3 times 2h plus h squared. Okay. And also, when we take the limit now, these last 2 terms are going to disappear. So all we're dealing with is actually 3 times 2 squared. And finally, we use our brain a little bit and we think, okay, what is 3 times 2 squared? That's 12. Okay. It is 12, right? Sometimes algebra is easier than numbers. Okay, yeah, it is 12. Good. All right. But let's read the problem again. Make sure we're actually answering the problem. It says find the tangent line. Okay. So what we did is not enough. We found m. We found the slope of the tangent line. We need to find the rest of the tangent line now. So this is m. We also want to find the tangent line at x equals 2. So we need a point. Our point is 2 comma f of 2, whatever f of 2 is. Well, we just plug it into the function definition, or plug it into the curve that we're trying to intersect at, and we get 8. Okay. So the point that lies on this curve lies on the function is 2 comma 8. And we can write the point slope form of this. Y minus 8 is 12, x minus 2. And there we go. That is the answer we're after. So any questions on this? Okay. Well, then this is the last problem for today. Same process. We just have a different type of function now. And so you can kind of expect that we're going to need to use, what's it called? Conjugate, multiplying by the conjugate in this last problem. So we start, what are we trying to compute? Problem says f prime of 2. Okay. Take the limit, recall the limit definition of derivative. So f of 2 plus h minus f of 2 all over h. Okay. Now we replace the f by what it's defined to be. So I'm plugging 2 plus h into this function, replacing this x by 2 plus h. We get square root of h plus 4. Okay. Next, I plug in 2 into this function. I get square root of 4, which is just 2. Okay, and this is all over h. Now, right, so I already told you the trick, but you stare at this guy and you need to realize you can't just plug in. You have to use some kind of trick, some technique to calculate this limit. And that particular trick is multiplying by the conjugate. So we go ahead and write down the conjugate. Hopefully you remember that because that was on the previous homework set, I think. So you just flip the sign that separates the things, and you get this. And you have to multiply top and bottom by the same quantity. Otherwise, you end up completely changing your expression, which is not allowed. Okay, so here we have that. And we can compute the numerator really quickly because we know what multiplying by the conjugate does. It is a special thing that lets us get rid of the middle terms. So the middle terms disappear, and all we have to do is compute this square root times this square root, which is just going to square away the square root. And then the -2 times the +2, which is just a -4. And so this is really, if you expand it out, that's exactly what you get. And the denominator, you just multiply across. Okay. And lastly, we can just cancel and cancel. So the +4 and the -4 will cancel. You'll be left with an h on top. And all right, maybe I will, for this one, I'll just cancel. Okay. We can skip a step, I hope. So this cancellation is going to leave us with a 1 on top and a square root of h plus 4 plus 2. And now we can plug in. When we plug in, we get square root of 4 plus 2. 2 plus 2 is 4. 1 over 4 is what we get. And so that's it. Okay. So are there any questions on anything?
I had a question on number 10.
Okay.
Just a quick question. So
Mm-hmm.
we got 18 feet per second, right?
I can't. Okay. So yeah. Mm-hmm.
Okay, and that's like our slope right in that moment.
Mm-hmm. Yeah.
Okay. That was just my question. I just want to make sure I'm thinking about this right.
Yeah. I mean, I guess you're trying to map the intuition, right? So, I mean, I'm not sure exactly what your real question is. There's definitely a hidden question, right? That you're not saying. But if you map this onto like physics, you know that the ball is traveling with a parabolic trajectory, and the rate of change, like its velocity is going to be changing, but the acceleration is constant. So yeah, in that precise moment, it's traveling at a rate of, like, it's going up at 18 feet per second, but gravity is affecting it, and it's going to slow down the velocity, and eventually it's going to start falling downwards. I don't know if that's helps to.
Yeah, that's how I was thinking about it. I was just making sure I was like thinking of like derivatives correctly, I guess.
Mm-hmm. Yeah. Yeah, in this situation, this is a velocity. The derivative of a height function is going to give velocity. Derivative of a velocity function is going to give acceleration. So yeah, maybe we'll see a bit more of that when we get to like applications. So, okay, good. Other questions? Well, if not, then I'm going to stop recording and we can end for today.